the difference between electronegativities of A and B will create the partial charge delta minus and delta plus. So we'll create the bond dipole, which is by definition parallel vector to the bond directed from the plus to the minus, and the intensity mu equal the absolute value of delta times the distance between A and B, the internuclear distance. As the difference of electronegativity between A and B increase, that means the electrons are more attracted to one than the second. That means delta minus and delta plus will increase in absolute value. That means the bond dipole increase. So as the difference delta En increase, delta increase, bond dipole mu increase. What is the meaning of the bond dipole increase? The bond dipole increase means the bond is more polar. And the bond is more polar, that means the bond is more ionic, or the bond is less covalent. So now we have to calculate, since delta En of the bond HCl is 0.9, which is between 0.5 and 2. So we have to calculate the percent ionic of this bond and the percent character of this bond, since the bond is polar covalent. Ionic character and covalent character. If a bond AB is polar covalent, that means this bond is not 1% ionic nor 100% covalent. It's not 100% pure ionic nor 100% pure covalent. So the bond AB has a certain percent of the ionic character and another percent of the covalent character, and the percent ionic plus percent covalent for the bond AB is equal to 100. So now, how to calculate the bond, the percent ionic and the percent covalent of the bond? Pay attention. If we find the difference of electronegativity between 0 and 0.5, so the bond is 100% ionic, 100% covalent, 0% ionic. If the difference of electronegativity is between 2 and 4, the bond is 100% ionic, 0% covalent. And since the difference is between 0.5 and 2, so we have a value of ionic character and a value of covalent character. How to calculate this percentage of ionic and covalent character? First of all, I will suppose that the bond AB is 100% ionic. I suppose. That means the electron has been transferred completely from A to B. So B gains the charge of one electron. So the charge delta, the absolute value of the partial charge, is the charge of one electron. So absolute value of delta is equal to absolute value of E. I repeat, I suppose the bond AB is 100% ionic. So the electrons are not shared between A and B in this case. The electron is transferred from the lower electronegative, supposed A, completely to the higher electronegative, which is B. So the electron has been completely transferred to B. So B gain a charge which is equal to the charge of this electron gained. So delta, absolute value of delta, is equal to absolute value of E. In this case, the bond dipole for a bond supposed 100% ionic is equal to the charge delta equal absolute value E times the distance AB. Then we do the cross multiplication. If the bond is 100% ionic, so we have a value of mu 100% calculated 1.6 times 10 minus 19, which is the charge of the electron in absolute value, and the distance AB is given, so I can calculate mu 100%. What is the meaning of mu 100%? If the bond is 100% ionic, it will have a value mu 100%. For the mu experimental or the mu given or the real value of mu AB, for mu experimental, I can find directly the percent, the real percent ionic. So for mu 100%, we have 100% ionic character. For mu given or for mu experimental, I can calculate the percent ionic, which is equal to mu experimental times 100 divided by mu 100% ionic, which can be calculated. And in this case, we can find the percent ionic. Then the percent covalent is equal 100 minus percent ionic. You can use directly this formula without a proof. The percent ionic is equal to mu given or mu experimental or the real bond dipole divided by the bond dipole of the bond supposed 100% ionic, which is equal absolute value E times dAB times 100. Okay, so percent ionic is equal percent experimental divided by percent 100% theoretical ionic times 100. And the percent covalent is 100 minus percent ionic. We pass to Lewis structure. Lewis used dots to represent the valence electrons, and the notation is known as Lewis dot symbol. In the Lewis theory, LT, we are not interested about core electrons. We are interested about only the valence electrons which are responsible for the bond. Lewis usually use 4 orbitals for block S and P. Why he used 4 orbitals? According to the quantum numbers, the S is 1 orbital and the P is 3 orbitals. So in block S and the block P, we have maximum 4 orbitals, 1s and 3p. And in each orbital, we have 2 electrons. So Lewis use 4 orbitals, use 4 rooms. In each room, we can have maximum 2 electrons. So 2 times 4 equal 8 electrons maximum, and this is the octet rule. The octet rule means the orbitals completely filled. So according to Lewis, any atom that enter a bond will tend to have 8 electrons around itself in order to have its orbital completely filled or to follow the octet rule. But pay attention that we have a lot of exceptions to the octet rule. For example, consider sodium. Sodium has Z equal 11, 1s2, 2s2, 2p6, 3s1. So in the level 3, I have only one electron. I have one single electron. So Lewis represent this sodium by Na. He put one dot. This is, pay attention, this is a notation. This is man-made, and this is not a true fact in the structure of the sodium. Instead, to say that sodium has one valence electron, I can represent by Na 1 dot. Consider Cl. Cl has 7 valence electrons. So I put 1, 2, 3, 4. This is Hund's rule. I fill the rooms by 1 electrons, then I complete the cycle. So I put 1, 1, 2, 3, 4, then I redo the cycle. So we obtain 4 rooms, 3 rooms containing 2 electrons, and 1 room contains only 1 electron. So this is to say that Cl has 2 plus 2 plus 2 plus 1 has 7 valence electrons. What is the Lewis representation for sodium Na+? The sodium Na+ is obtained from sodium by losing 1 electron. So the configuration, the electronic configuration of Na+ ends by S2p6. So around sodium we have 8 electrons. 1, 2. This is for chloride. For sodium, I lose this electron. So in the lower level, I have 6 valence. For Cl-, Cl- is obtained from Cl by adding 1 electron. So I can add this electron at this point. So we have 2, 4, 6, 8. Pay attention that the brackets and the minus are notation in order to make the difference between this Cl, which is Cl-, and the first, which is Cl atom. So in Cl-, I have 8 electrons. This minus and this brackets are only notations to make the difference with the corresponding atom Cl. So the covalent bond can be represented according to Lewis. For example, consider H2. The first has 1 valence, the second has 1 valence. Due to the bond HH, we will have sharing of electrons between the 2 hydrogen. These 2 electrons are count 2 for the first and 2 for the second. And the hydrogen follow the duet rule and not the octet rule. So these electrons are called bonding electrons or pair of electron bonding and can be represented by 2 dots, but we prefer to use the dash for bonding electrons. Consider Cl. The first Cl has 7 valence and the second Cl has also 7 valence. So the first Cl need 1 electron to have orbitals completely filled, and this is the same for the second. So the first Cl will present its valence electron, 1 valence, and the second will present 1 valence, and we will have 2 electrons between the Cl. So if we count for the first Cl, we have 2 4, 6, 8 electrons, and for the second Cl we have also 2, 4, 6, 8 electrons. But we have to make difference between these types of dots. The two dots that are not responsible or not involved in the bonding are called non-bonding electrons or non-bonding pair. And the dots responsible for the bond are called bonding electrons or bonding pair. For this reason, I prefer to make the difference between the bonding electrons and non-bonding electrons. The bonding electrons use instead of dots the dash, and for non-bonding electrons use the dots. Lewis dot theory. So the atom only come together to produce a more stable electronic configuration, which is the orbitals completely filled. We have 7 and 7. This is step 1. Step 2, the atom bonds together by transferring of sharing electrons. So we have 7. We need one more electron. These two atoms will share these 2 electrons. Many of atoms like to have 8 electrons in their outer shell. This is the octet rule. And pay attention that we have a lot of exception. So step 1, the 2 atoms will be closed. Step 2, they will share electrons. Step 3, the shared electrons are between the 2 atoms, and these shared electrons are count 2 for the first and 2 for the second. And as I said, I prefer to use for bonding electrons, we prefer to use dash. And for dots, keep it dots and not dashes. You can put dashes, but I prefer dash for bonding, dots for non-bonding. How to find the Lewis dot structure for a polyatomic molecule? First of all, we have to follow these rules and pay attention that in the chemical bonding or in the bonding theories, the key is the Lewis structure. In the second part, we will study how to find the geometry of a molecule. To find the geometry of the molecule, first of all, we have to draw Lewis structure of this molecule. And if Lewis structure is incorrect, that means the geometry will be incorrect. So pay attention how to write or how to draw the Lewis structure for a molecule. First of all, count the total valence of electrons of all atoms. This is step 1. Step 2, determine the central atom. Suppose I have A, B, C. I have atoms A, B, and C in a molecule. How to draw Lewis structure? I have to count the valence of A. How to find the valence of A? If I know the group of A, or if I know the place of A in the periodic table, I can find directly its valence. Group 1 has 1 valence. Group 2 has 2 valence. Group 3, 3 valence. Group 4, 4 valence. Group 5, 5 valence. Group 6, 6 valence. Group 7, 7 valence. Group 8, 8 valence. So if you know the total valence, you count the valence of A, the valence of B, the valence of C, then you add, you obtain the total valence electrons. Step 2 is to determine the central atom. I have a molecule containing A, B, C atoms. Which is the center, A, B, or C? In general, the central atom is that with large number of single electrons. This is in general, and we have exceptions. If we have more than one central, use the order of the formula. Suppose you have two centers, you use the order of the formula. Step 3. Place 2 electrons to join the bonds. Okay? Suppose I have 3 atoms and I have 16 electrons total. To join A and B, I need 2 electrons. And to join B and C, I need 2 electrons. So from that 16 total, I need 4 electrons to make the bonds. The remained valence electrons are distributed on the outer atom. I will do an example. I will do an example on the sketchboard now. But you have to know the rules. Step 1, count the total valence. Step 2 is to determine the central atom, which is in general with the large number of single electrons. Steps 3, from the total valence electrons, take 2 electrons and put between 2 atoms in order to make their bonds. Suppose I have 16 electrons and I have a molecule ABC. I have to join A to B, so I need 2 electrons. B to C, I need 2 electrons. So the remained is 16 minus 4. I have 12 electrons remained. The remained electrons will be distributed on the outer atoms in order to have the octet rule or to have orbitals completely filled. When you fill the remained on the outer, if you have also remained electrons, you put it in the central. I will do an example in order